All right, guys, we made it to the last chapter of the year. That's got to be a good feeling. So today's lesson is actually just a pre-calc lesson because this whole final chapter is about vectors and how we can tie vectors into parametric and polar functions. But as of right now, most of you don't know what a vector is. So the goal of today is to kind of introduce you to first three-dimensional coordinate systems, and then after that we will throw vectors into the mix and relate the two. Okay, so today three-dimensional coordinate systems, and then 10.2 more on vectors. All right, so three-dimensional coordinate systems are super important to understand because we live in a three-dimensional world, right? So we kind of need to understand the science behind this. So let's establish some rules first. In a three-dimensional coordinate system, we have an X, a Y, and a Z plane. Okay, so you can imagine there's something called the right-hand rule to kind of visualize and imagine this. So essentially, take your hand, make a fist, and take your first finger, your index finger, and point at yourself. Also in that fist, make sure your thumb is up, like shown in this picture here. So make a fist, thumb straight up, index finger pointing at yourself. Your index finger would designate the x-axis in a 3D plane. Your thumb would designate the z-axis going up. And then the y-axis would be like your palm of your hand and your wrist, okay? So X always comes out towards you, Y kind of runs along the paper, and then Z is going up. Here's maybe a better indication of the XYZ coordinate plane. So if I'm looking at, the axes in relation to a room, the floor would be the XY plane because it's where the X and the Y axes meet. The right or back wall would be the the YZ plane. That's where the axes meet. And then the left wall would be the XZ plane. Okay, so those are your three dimensions. You know how in a two-dimensional coordinate system, an XY axis, we have four quadrants, right? We have four quadrants. In a three-dimensional coordinate system, we don't have quadrants anymore. We have octants. Okay, we have octants. So the purpose behind the change in the name just means, oct means 8. There are 8 different sections now instead of 4 because you're in a three-dimensional system. So it's called octants. The first octant is where everything is positive, and that would be the one that you're seeing now. Okay, how do you plot a point? So to plot a point in the XYZ coordinate plane, you would move in the X direction, Y direction, and Z direction. Okay, so if I wanted to plot the point A, B, C, if they were all positive numbers, you would come forward on the X axis, you would come out to the right on the Y axis, and up on the Z axis. Okay, so it's forward, and then left or right, and then up or down. Here are some examples with numerical values included. So -4, 3, -5. To plot this point, you would go, instead of forward, you would go backwards 4, you would go right 3, that's the Y direction, and then you would go down 5, that's the Z direction. Okay? This one, 3, -2, -6. You would come forward 3, you would go left 2, and you would go down 6. Okay, here's the challenge. We are trying to graph points, planes, etc. That are represented on a 3D space on a two-dimensional surface, right? We have just a flat piece of paper and we're trying to graph these points. So it is going to be challenging to make it look right, okay? So you're going to have to modify things at times to make things look a little bit more clear. Let's actually start with B. So it says, what surfaces in R3, that means 3 dimensions, are represented by the following equations? So like, what does y = 5 look like in a 3-dimensional space? In 2 dimensions, this is a straight horizontal line. But in 3 dimensions, it's something very different. So I'm going to try to graph it for you. Please be patient because I'm drawing this with a wireless slate and it's not real easy to do. So I'm going to call this the z-axis, and I'm going to go x and maybe y like this. And I want to mark the y-axis 1, 2, 3, 4, 5. Okay, so my y-axis at 5 is right here. Okay, y equals 5 means that x and z can be anything, but y would have to stay right at 5. So the y values would have to kind of come in and they would have to run through parallel. So anything on the x-axis would be anything that goes forward or backwards, right? So x can be anything, but y has to stay at 5. So this line would exist, but you also could have z as anything. So you could go up or down as far as you want to, as long as you're staying parallel to that y equals 5 value. Okay, so what is happening is the y equals 5 equation is actually a plane, okay? It's like taking a slice, piece of paper, if you will, and kind of standing it vertical and cutting it right through when y is 5. So this is supposed to be a plane. This is a plane. And this plane is actually parallel to the XZ plane. So if I'm talking about like in a room, this would be like the left wall, this XZ plane. This y equals 5 equation, y equals 5, is parallel to that. All right, so let's try the z equals 3. So z equals 3, you're going to go through the vertical z-axis, the one that goes up and down. You're going to mark it at 3, and you're going to make another plane, okay? But this one's kind of hard to draw because you're trying to make it look like it is parallel to the floor, I guess. So this one just kind of, again, bear with me. It's not real easy to draw planes in a 2D surface, but the idea is we're going 1, 2, 3 units up the z-axis. We're going to mark it, okay? And then anything that is equal to z, so I could come forward as far as I wanted. I could go backwards as far as I want, and I still would stay at z equals 3. And I can come left and right also. Okay, so I'm kind of making a sheet of paper, a plane, and this one's running parallel to the floor in that first picture, but in this, the floor is referring to the x or xy plane. So this one is a plane that is parallel to the xy plane. Parallel to the xy plane. And this one is called z equals 3. Okay, here's a better drawing for you. So here's z equals 3. This is that flat surface that I was trying to draw. This is a little better because computers can do things better than us. Here's y equals 5. But then this third one is y equals 5 in a 2-dimensional coordinate system. This is what we're used to, xy axes. Y equals 5 is just a straight line, but now it's a whole plane. Okay, describe and sketch the surface in R3, 3 dimensions, represented by the equation y equals x. Okay, so let's review real quick. If I was just talking 2 dimensions, oh my gosh, cannot draw. Let me just pretend that didn't happen. Try again. If I'm talking about 2 dimensions, y equals x. Can't draw a straight line to save my life. Y equals x would be a line with a slope of 1, and this is y equals x in the 2-dimensional space with x and y being here. Now I got to try to draw it in 3. So I think maybe what I'll do is I will kind of adjust my axes a bit. Just kind of rotate a tiny bit. Okay, there's X, Y, there's Z. So to graph X or Y equals X, what you would want to do is you would want to think about where X and Y are equal in value. So if I went up 1 on X and over 1 on Y, that would be a point on the plane we're about to draw. 2 up 2 on X, over 2 on Y, same thing. So kind of right dead center of X and Y would be where X and Y are equal. I'm going to be able to draw a straight line at some point today. We'll pretend that's a straight line, okay? Keep in mind, as long as X and Y are equal, Z can be anything because Z is not identified in this equation. So essentially, here's your baseline, and then you could go up or down as far as you wanted to go, and that would still be a solution to this equation, okay? So go up or down as far as I want to go, and that's going to create a plane that's kind of running straight in between the X and the Y axes. All right. So just a quick one more thing about this. X and Y have to be equal for Y equals X for that to describe that plane. But again, Z could be any number. So 2, 2, -3 could be on this plane. -1, -1, 5 could be on this plane. Again, the only stipulation is that the X and Y values have to be the same. All right, so something else that is helpful to know, this is not really a calculus thing, but this is something helpful to know, is how to find the distance between points in a three-dimensional system. So you guys know, you know how to find the distance between 2 points in a 2D system. It's not that different for the distance between points in a 3D system. So essentially what you've got going on here is you've got like Pythagorean theorem almost, distance formula, if you will, with one more component for the Z dimension. The proof I'm not going to walk through right now because it's time consuming, but I will make sure that I add this on and post it with the PDF of the notes. Okay, so let's just practice that formula real quick. The distance from point P to point Q. So we want to find the distance between those points. So to set that up, we're going to do the difference between the X values. So I'm just going to start with P to Q. So 2 minus 1 squared. Difference between the Y values squared plus the difference between the Z values squared. So that's your setup here. And then it's just arithmetic, right? So this would be 1 squared is 1. This would be 2 squared is 4 plus another 2 squared, which is 4. So it looks like we're getting 3 as the distance between those 2 points, 3 units. Okay, find an equation of a sphere with radius r and center h, k, l, meaning like the x value, the y value, the z value as that ordered pair. So what you would do is you would want basically to make this like a distance formula, okay? So instead of, you know, we have distance is equal to the square root of, like we said, the difference between the x values squared plus the difference between the y values squared, right? You know this. We can just apply it to this sphere. So instead of d, the distance between these points would be representative of the radius. And then one of the x values is called x, but the other one is called h. So we would write x minus h squared. And then same with the y's. The y value, one is y, one is k. And then the other z value is, we're calling it L. So here's an equation that represents this sphere. It's not in standard form. Standard form for circles and spheres, usually you don't have a radical. What you would do is you would square both sides to make the radical go away. And so r squared equals all this stuff under the radical would be how you write an equation of a sphere, okay? So if you knew the center of the sphere, so let me just make an example down here that's not written. If you knew that the radius of the sphere was 3 and it was centered at, I don't know, 3, 4, 5. If the center of it was at 3, 4, 5, you would just plug those values in. So you would get 3 squared, so 9 equals, and it would be x minus the x coordinate plus y minus the y coordinate plus c, and then so just filling in the x, y, and z values, that would be the equation of a sphere with a radius of 3 centered at 3, 4, 5. Okay. Example 5, show that x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 equals 0 is the equation of a sphere, and find its center and radius. Essentially, we got to take this huge long thing and turn it into this format. Okay. Fun fact about me, I love questions like this, but I also know that I am not normal. So I love these questions because these are basically little algebra questions. It's just a nice break from calculus, you know, and not real complicated. Anyway, to kind of fill you in on what I am doing is I am setting this up in sections. So I'm putting the x's together, the y's together, and the z's together. And what I'm also doing at the same time is I am leaving a space, because essentially my job is to put each of these into their own terms that are perfect squares. So to do that, I'm going to have to do completing the square for every single variable, for the x's, the y's, and the z's. So quick refresher course, completing the square, you take half the middle term and you square it, and that tells you the value to put in this missing spot. So 4 for this one. Half the middle term squared for the y value looks like it's going to be 9. And then over here, we're going to be at 1. So that's the values we need to be able to make these perfect squares that are factorable. But the 4, the 9, and the 1 did not exist in the original equation. So you have to balance by adding 4, 9, and 1 on the right side of the equation as well. Then you're pretty much done at this point. All you have to do is take your trinomials you've created and factor them as perfect squares. So this would be x plus 2 quantity squared, y minus 3 quantity squared, and then z plus 1 quantity squared, and that is equal to negative 6 plus 4 plus 9 plus 1. That should be 8. Okay, so we did part 1 where we just verified that this does fit the mold for equation of a sphere. And then the second part said find the center and the radius. So the center is located at the opposite signs of what's given here. So this would be negative 2, 3, and negative 1 is the center. The radius is equal to the square root of the number over here. So the square root of 8, which is the same as 2 radical 2 if you wanted to simplify. That's the radius of the sphere. Okay, one last thing. What region in R3, 3 dimensions, is represented by the following inequalities? So we have to visualize, and this is kind of hard. I have the picture right here. I'll show you in a minute because I'm not going to be able to draw it in a way that makes sense. So step 1, I'm actually going to split this into 2 separate equations, inequalities. So what we have is x squared plus y squared plus z squared is greater than or equal to 1 or less than or equal to 4. And then we also have that z is less than or equal to 0. Okay, now take out the inequality part of it. X squared plus y squared plus z squared, that is set up to be descriptive of an equation of a sphere. Okay, so both of these are describing a sphere. What is this number in a sphere equation? What does this number represent over here? That's the radius, right? So the first inequality is saying that we have a sphere centered at the origin, but the radius has to be greater than or equal to 1. Okay, so think about a ball, a sphere, but the radius is minimum 1, but larger than that, right? Down here you have the same sphere centered at the origin, but the radius of this one would be 2, actually, because it's the square root of this number. So you have a sphere that has a radius bigger than 1, but smaller than 4. So essentially what you have is you have a ball that is no bigger than a radius of 2, but it can't have a radius less than 1. So essentially there's kind of like a hole in the center of that ball. It's hollow inside, with the radius being 1 to 4, nothing less than 1. That's why there's a hole in the center. This third inequality says z is less than or equal to 0. So if you have a sphere that's centered, let me go back. If you have a sphere that's centered on the coordinate plane, but z has to be less than or equal to 0, that means like half of the ball is missing, right? Because you can't have anything that comes up above the xy plane. Okay, so it's a sphere that's hollow in the center, but only half of it is shown. Let me put the picture up and show you. So this part here in the middle would be hollow, and then it's obviously only half of the sphere because the top half doesn't exist according to this inequality. Okay, that's it. You have a homework assignment in the book to review these topics, and then in section 10.2, that's when we'll start to tie calculus and vectors into this concept.